Welcome to the High Performance Best Practices for Websites session today. My name is Jason Weber. I'm a lead program manager on the Internet Explorer team at Microsoft, and my focus is performance. How many of you were in the keynote this morning? Almost everyone. How many of you saw the work that we're doing today? It was announced this morning around hardware-enabled HTML5. A lot of hands there. A lot of excitement throughout the day in that space. Now, today, we're gonna cover two things in this session. The first is really best practices for improving your performance for your websites today. And we're going to do that by looking at really three things. We're going to start by looking at taking an inside look at the browser. We're going to look at the subsystems that make up the browser and really look at how the browser operates. From that, we're going to look at 20 best practices that you can use today, 20 very specific things that you can go back and apply to your sites today that are going to improve performance of your websites across all browsers. Now, of course, I work on the Internet Explorer team, and I have a deep understanding of Internet Explorer. But the practices that we'll be looking at today apply to all browsers. Many of the practices that we'll be walking through are discussed broadly on the Internet. And one of my goals today is not just to show you the practice, but give you a better understanding of the principles behind the practice so that you can apply those principles in everything that you do. The second half of this session, we're going to look at or give you a preview of Internet Explorer 9 and the performance characteristics that are changing. This goes back to the hardware-accelerated HTML5 that you saw during the keynote that I just mentioned. And hardware-accelerated HTML5 is really enabled by two different things. The first is GPU-powered graphics, and the second is compiled JavaScript. And we'll go deep into that in the second half of the session. So let's go ahead and get started with the first piece, best practices that you can use today. And I wanted to start with the disclaimer, which is I have a lot of content. When we were preparing for MIX, all the presenters received an email, and one of the comments in the email recommended that presenters keep their presentations to about 25 slides. I have to warn you that I actually have, I think, 95 or 100 slides. That's because I want to show a lot of code samples. I want to show a lot of pictures. I want to give you guys not just a bulleted list of things to do, but I want to actually show you the best practices in action so that you can take those back. My presentation will be linked on the MIX website next to the video, so you can go down download the presentation later. You can actually play with these best practices yourselves. You don't have to worry about taking notes across all 95 slides today. Now, as we start talking about best practices, I thought I'd start with a scenario. And the scenario I chose is loading a news website. And I picked the Wall Street Journal. We could have picked any of a large number of different news websites, or I'm guessing many of the websites that you have today exhibit the same performance characteristics as these news sites. But I picked the Wall Street Journal. And here we are on Bing.com. And what we're going to do is we're going to navigate in the address bar to the Wall Street Journal. And the experience that your customers have today for many web properties, and really what as web developers are trying to optimize is this loading experience. In the Wall Street Journal's case, the thing that you see is it kind of first flashes to black. The HTML has come in. We know the background color. The browser is able to kind of erase the screen and paint it to black. And as additional information comes in, we're able to progressively display more and more information. The initial HTML comes in with some text. A couple of images were pulled from the cache. The headers start to appear as more style information comes into the page. The initial content will appear. After a split second, the right column starts to appear. The right column in this case is actually programmatically composed from JavaScript and is injected into the page. Additional content, such as media, trickles in over time. And as the media came in, you'll notice it actually caused the content shift down. It caused the page to shift down a little bit. Customized content on a per user or per locale basis comes in. In this case, stock quotes, as well as some local content. And finally, advertisements appear. Now, once the web page is loaded, customers interact with the page. They might start playing the video. They might actually toggle through the different headlines. as well as the page is going to interact with the customer. It's going to change the advertisements. It's going to update the stock quotes. It's going to update the headlines. This is the performance scenario or this is usually what, when your customers talk about performance, this is an example scenario of what they're referring to. Now, I picked the Wall Street Journal, but I didn't necessarily want to go, and show you the underlying characteristics of the Wall Street Journal. I wanted to do that across a few different news sites and give them a little bit of anonymity. So here you'll see 10 different news sites on the left. And what I've done is I picked 5 of these, and I spent a bunch of time profiling those news sites. And I'm going to call those news site number 1 through number 5. The last thing I want is a newspaper or a reporter upset with me for picking on their site. So I have news sites number 1 through 5, and we're going to look at these in a little bit of depth here. Here are some of the characteristics of those news sites that I picked. Again, these are some of the top web properties in the world. And you'll see that if we look through the columns left to right, the left column is the total size in kilobytes of content that's being downloaded from that news site. The next is the number of HTML elements that are in the page at the end result of the page. We then have the total number of CSS rules that are brought down and being applied to the page. The number of images, the number of script files, the total number of lines of script in the page, and then last is the script libraries that page uses. Many of them use standard libraries such as jQuery or Prototype or YUI, the Yahoo UI library. Others have their own custom script libraries. Now, let's look at some of the kind of interesting variations that occur across these sites. If we just start with the total size, you'll see that news site 1 is 10 times larger than news site number 3. 3 megabytes compared to 300 kilobytes of content. That's very significant for 5 websites that are really producing the same type of experience to customers. If we go and look at, for example, the number of elements to the number of CSS rules, you'll see that news site number 1 has 8,600 elements for only 1,300 rules. So about 6 elements for every single rule. Whereas news site number 2 has 820 elements for close to 3,000 rules. So architecturally, they have the complete opposite architectures in place just in terms of elements and rules. If we go on to image files, you'll see that news site number 1 has 137 images, whereas news site number 2 has only 26. So very significant differences. If we look at the amount of script, news site number 2 has only less than a quarter of the amount of script of news site number 5. And then finally, news site number 4 links in a whole bunch of different JavaScript frameworks. News site number 2 doesn't. Again, news site number 2 only has 3,800 lines of script, and they've optimized that script. So based on the information you've seen today, what site do you think loads the fastest, provides the fastest page load time? 2? I've heard 3 or 4 2s, a couple 3s. It's actually site number 3. And we'll talk about why as we go through the best practices section of the presentation. Now, I have to ask the opposite question. Which site loads the slowest? 1, 5, 4, 5, 3? I've heard a lot of 1s and a lot of 5s. It's actually site number 4, which at first might be surprising because you'll notice site number 4 has half the total content that comes down compared to site number 1 and site number 5. It has half the JavaScript. The smallest number of CSS rules across any of these sites. And the reason for this is that site number 4 doesn't really follow any of the best practices or many of the best practices that we're going to talk about today. This is actually a view on the page load times broken out by the subsystem timings inside Internet Explorer. I think as many of you know, and as was discussed in the keynote today, performance is a multidimensional problem. Internet Explorer is composed of 10 or 11 different subsystems that we're going to talk about today. And you can see where the time is spent. Of course, if you look in red, that's the amount of time spent in the JavaScript engine. Purple is the amount of time spent in rendering or displaying the content to the screen. But you can see that each of these 5 sites have very different patterns in in where the time is spent. If you take that content and you average it together, you can see that this is kind of the average across all of those 5 news sites. And the question a lot of people get is, well, those are news sites. They're relatively static content with a little script. What about Ajax sites, right? These rich sites that we as developers build. And so we went and looked at the data for some of the top Ajax sites in the world. Gmail, Hotmail, Google Docs and spreadsheets, the Office web applications. And what we did was we averaged those together, and we see a pie chart that looks something similar to this. Now, the proportions change, but you'll see that performance is still greatly impacted by all of the subsystems. Here are the subsystems that we're going to look at today. And in this slide, there's actually 11 of them, starting with networking. And I'm going to walk you through each of these 11 subsystems. I'm going to give you an idea of what the subsystems are and what they do. And I'm going to show you some best practices for optimizing your content in those subsystems. And these are the 20 best practices that we would strongly encourage you to start leveraging today to improve performance. We'll start with networking. The first best practice is to compress network traffic. Here you see a very typical HTTP request and response. And you'll notice, though, that on the left, we've specified that we accept the gzip encoding. And on the right, the response sends it back to us as gzipped content. This is standard technology that all servers support today. And you'd be surprised at how many customers or web developers forget to set the right zipped content on their sites and are actually losing from compressing their network traffic. Now, there's one exception to this best practice, which is that you should not compress images. Images are already compressed inside the file format itself. And by actually compressing it again through gzip or another compression technology, what ends up happening is, in best case, you'll end up with an image that's the same size. In worst case, you'll end up with an image that's actually larger. And you'll force the browser, all browsers, to spend a bunch of time decompressing the image when it arrives down. So the best practice is to compress network traffic, except for images. The second best practice is really to provide cacheable content. How many of you provide cacheable content today across your web properties? It's a surprisingly small number of hands. And when I talk with customers, many times customers who think that they're providing cacheable content, when we go in and look, in many cases they're not caching as much as they need, and that's often because they're a little bit worried about updating content on the server or the impacts of caching. And here you'll see on the left we have our first request and our first response. And in our response, it specifies that the content is not going to expire for some period of time. So in this case, the content's not going to expire until this Friday. So by doing this, the browser is able to cache the content and will pull these images or content out of the cache. In this case, it's an image, rather than requesting it again from the network. And here you can see kind of the second request, and we don't have to pull it. The next best practice is conditional requests. And conditional requests allow you to specify content that may be modified from a certain date. So in this case, the request goes out, and it says, if the content has been modified since the last time I downloaded the content, send down new content. But if it hasn't, go ahead and pull from the cache. And in the response, it'll return when that content was last modified so that the browser knows what to do. Now, in addition to kind of compressing the content, you can actually use techniques to compress inside the content itself. So in this case, the best practice is really to minify your JavaScript. On the left, we have our original JavaScript source code for one of the routines that's actually on the test drive website that we just released. And if we were to minify that, and what the minification process does is it goes through, it removes all the spaces, it takes the variable names and collapses them down to single characters. It actually sometimes compresses the call patterns that are used. By minifying that JavaScript, we can actually decrease the amount of script by up to 75%. So your resulting script in many real-world scenarios can be about 25% of your original script size. And as JavaScript becomes more and more important and is more broadly used through the rich frameworks that are out there, the minification process becomes more important. The last best practice that I wanted to share, and this is one that really feels like common sense, but you'd be surprised at how often people forget to do this or make this mistake, and that is not to scale images. Scaling images has, in this case, let me show you what I mean. So we have a logo that's 500 pixels by 400 pixels wide, but when we go to use it, we're only using it 50 pixels wide by 40 pixels tall. Not scaling images, starting with kind of an image of the actual size that's going to be used allows you to send less content over the wire, and it also requires less CPU time for the browser once the image has been downloaded. So in this case, we could use Photoshop or another image program and start with a 50 by 40 image. Of the news sites that I mentioned, 3 of the 5 news sites on their homepage are actually scaling images. And the last network optimization, which is really an extension of scaling images, is using image sprites. Now, if you remember, one of the news sites was using about 120 different images. And that's because every little icon on their page was a separate image. This comes with overhead in the size of the image file. It also increases the number of network requests that occur. By using an image sprite, and for those of you who are not familiar with image sprites, it's really a technique to take multiple images and put them into the same image. By using an image sprite, you're decreasing the total number of bytes going over the wire. You're also decreasing the total number of network requests. You're allowing the images to get to the browser sooner. And in doing so, you're improving the performance of your overall page. Once that large image has been downloaded, the technique you can use is using CSS techniques and divs. You can actually use that same image and move it around on the page to position it in the correct location to just show the individual image that you need. I wanted to show just one Internet Explorer 9 feature which we've added this release, which is the new network tools, which help you really understand and improve networking performance for your sites. For those, how many of you had a chance to download the platform preview release of Internet Explorer 9? Just a couple of hands. The platform preview release, and as the tools that you saw in the keynote today, the developer tools are included in the platform preview release, and they include our new networking tool, which allows you to look at all your network traffic and even go into the very specific details around the headers, requests, and responses, and how that content is being used, how it's being cached. So let's move on to the second browser subsystem, which is the HTML parsing subsystem. When the initial request goes out and the HTML comes down, this is the first piece of the browser that really comes into play with regard to performance. The browser starts parsing the HTML, and as it encounters files that need to be downloaded, it's going to go fire off those downloads. There's a few things that can block the browser from downloading additional content or from parsing. This is less true in Internet Explorer 8 and some of the modern browsers that you might be targeting. But this is a concern for some of the older browsers that are still broadly used across the internet. One of the things that can actually block parsing and impact is inline JavaScript. So in this case, you'll see that we have some inline JavaScript in the head. With some of these older browsers, what happens is when they encounter the JavaScript, they actually have to go and execute that JavaScript before they can move on. And that's because the JavaScript could actually be doing something like a document.write and manipulating the remainder of the HTML content. So it can't finish parsing the HTML until that JavaScript's been executed, and that delays the initial page load. You should also avoid linking to JavaScript in the head of your HTML page for very similar reasons. In this case, what will happen is, particularly in some of these older browsers, when it encounters this script tag, it's going to go download the script file and execute it before it will continue parsing. The best practice is to link the JavaScript at the end of the file. This allows the browser to fully parse the HTML document, to download all of the images, and the images will be displayed to the user first, so they can be progressively rendered to the user and make your sites appear more quickly. And then the browser will download the JavaScript and execute it last. Now, there's some cases where you really must include your JavaScript in the head. Cases such as content management systems, if you're using some server-side frameworks, those frameworks may place your JavaScript in the head itself. In those cases where you must have it there, we recommend using the defer tag as a best practice. The defer tag has actually been supported since Internet Explorer 4. And what the defer tag does is it defers execution of the JavaScript until the page has been rendered and laid out displayed to the user. I do not know if Firefox supports this yet. So the third subsystem that really comes into play is the CSS parsing subsystem. As the HTML parser encounters CSS, it's handed over to the CSS parser. And there's a couple of really important best practices here that are very similar to the JavaScript best practices. And the first is to avoid embedded styles. This is less important in Internet Explorer 8 and some of the modern browsers. But this pattern can significantly slow down the performance of loading web pages, again, in some older browsers. But counter to linking JavaScript at the end of the file, the best practices here is actually to avoid linking your CSS at the bottom of the file, and instead to link the CSS at the head. What this does is it allows the browser to download the CSS immediately so that it has all the style information, and that style information can then be applied with the HTML and displayed to the user. Sometimes if the CSS is too low in a page, what will happen is you'll end up with a flash of what we call flash of unstyled content, where the web page will appear. It might appear with the right text, but it's not the right font, not the right colors, not the right locations. So include your CSS files at the top. And also, best practice is to avoid using the @ import for hierarchical styles. This is actually an external style sheet here. And at the top of the external style sheet, it includes, you can see, links to two external style sheets. Particularly in some older browsers that are still very common on the internet, what will happen here is when the CSS parsing is occurring, it'll hit the @ import, and it will have to go download first the style sheet 1 and then second style sheet 2 so that it can create the hierarchical cascade associated with them before it can finish parsing this CSS. For scenarios where you'd like to create hierarchical styles, we recommend multiple style sheets, again linked at the head of your HTML. The next browser subsystem is what we call the collection subsystem. I'm not going to recommend any best practices here today, because if we go back to our pie charts, it was the smallest slice of pie. But really, collections is, you think of it as a collection of attributes associated with your HTML elements. I'd like to move on to JavaScript, because there's a lot that you can do in your JavaScript code today to just improve performance. And the first and probably the most important best practices is to minimize symbol resolution. Symbol resolution is what a dynamic language runtime or a JavaScript engine does to map a symbol, such as in this case the variable foo, with the actual value of foo. And the way that JavaScript runtimes do this mapping is they work their way through a scope hierarchy. They'll start in the local scope being really where the script is currently, where the script is running. They'll work their way up through the intermediary scopes, and then finally, they'll go to the global scope if they're unable to find it lower, and resolve that variable in the global scope. The further away that resolution is from where it's used, the higher the cost. Now, I'll show you some examples of this in a minute. This is true for variables, but it's also true for members or instances. In this case, I have an object with a foo member hanging off of it. It's first going to look in the instance of that object. It's then going to work its way up the prototype chain. And then finally, it's going to have to cross over into the document object model if it's unable to find it in the chain. And in some cases, may actually need to create it. Now, let's take a look at two different examples on how to minimize symbol resolution. You can see that I have a function here with a local variable set to 5. And then my return statement is just going to take my local variable and add 1. You can see that my local variable, I didn't actually specify the var keyword. And so what happens in this case is it has to walk all the way up to the global scope to find that local variable. So even though I'm only using it in this function, it's actually a global variable. By adding the var keyword, I've then scoped it to local. This is a very common mistake that's made across many different websites, web properties today, even among sophisticated JavaScript developers. The next best practice, which is very closely related, is minimizing symbol resolution for functions. In this case, I have a worker function, and I'm iterating over a collection of items. And each time I call the function work, it has to resolve where that function is located. In this case, it's walking up that chain to find the function work. What I could do is I could create a function pointer. So I've created a local variable called funcWork, and I've set it to the function work itself. And then when I call that function, I'm actually referring to that local function pointer, and it increases the overall performance of this loop, in some cases quite significantly. The next best practice is to use native methods, in this case, particularly for JSON. How many of you use JSON today? How many of you use JSON by calling eval on your JSON when it's returned? Good. I only saw one hand there. Maybe it was a half of a hand. How many of you use a JavaScript framework to actually parse the JSON object when it's returned? Almost everyone. So the JavaScript frameworks are a very effective technique for using JSON. But what that means is that the JSON serialization and deserialization is occurring in script through script objects. By using the native JSON methods, which were first introduced into Internet Explorer 8, to do your serialization and deserialization, you can actually improve performance of this by some cases 5 or 6, a multiple of 5 or 6 times. And kind of finally, the last best practice for JavaScript is to remove duplicate script files. People often laugh when they hear this one. In this case, you'll see that we actually have 2 duplicate jQueries in the bottom. This is sometimes just a common mistake that people made accidentally. Sometimes people come across this and they don't realize there's a performance implication, so they don't address it. Sometimes it's the frameworks that you're using on the server as they compose components together will actually implicitly add in multiple script files. So really only send down the exact number of scripts that you need, removing the duplicates. And in doing so, you will improve the JavaScript performance because the browser won't have to parse and instantiate and in many cases, execute that code. Here's another example. And this is actually a real-world example that came from a customer about 3 months ago. They were having some performance problems with their site. And we went and looked. And you can see at the bottom of their page, they had included just about every JavaScript framework in the world. And when we were talking with them, it was kind of funny. They weren't even sure what frameworks they were using. They knew that they were using pieces for different frameworks for different pieces of their page. But in some cases, they didn't even know how the frameworks integrated together. Frameworks are incredibly powerful, but the best practice is to minimize the number of frameworks that you use, particularly on a page basis. And wherever possible, use the same framework for a particular pattern. So if you're using a framework for JSON, use that same framework so that you're only downloading one JSON parser. The next subsystem that I'd like to talk about is marshalling. And I put together a slide that shows kind of the concepts, some of the architectural concepts of Internet Explorer that'll help understand marshalling. If you think about the DOM, or the document object model, the DOM is actually part of what we refer to as Trident, or MS-HTML, which is the standard web platform that's used by Internet Explorer. The JavaScript engine is an external component. It lives in a separate DLL, and it's used by Trident itself. But when the JavaScript engine goes to talk with the DOM, it has to cross a boundary. And this boundary is what we refer to as marshalling. It kind of comes from the concept of COM marshalling, if any of you have C++ backgrounds. One of the analogies that we use on the team is that crossing this boundary is kind of like crossing a toll bridge. Each time you cross that toll bridge, it costs a little bit more money. And so you really want to minimize the number of trips that you have to take from one side of town to the other to save money or improve performance. The best practice is really to minimize the number of DOM interactions that you make from JavaScript. In this function, calculate sum, you'll see that 3 times I actually interact with the DOM. And all 3 times I call document.body.all. On the surface, this may look like 3 DOM interactions. But in actuality, it's 9 DOM interactions. And that's because I first call document. So I cross over to the DOM, and I get the document and bring it back to the script engine. I then have to call over to the DOM to get the body, bring it back to the script engine. And then finally, cross over the DOM to get all and bring it back. So this results in 9 lookups. The best practice is to cache those lookups locally whenever possible. So in this case, I have a variable elements, and I've cached that locally, and then I can reuse that later on inside of my function. And in doing so, I'm only performing 3 DOM lookups. Moving on to the DOM, which is on the other side of that marshalling tier. There's a couple of best practices that you can use to improve how you interact with the DOM, and specifically the APIs that you use in the DOM itself. The first best practice is built-in methods are always more efficient than trying to roll something yourself. In this case, I have the variable nodes, the nodes array, and I'm iterating through it. So I've gone up and I've gotten all the children of a particular node, and now I'm iterating through it myself. Instead of doing this, I could use a DOM API, such as next sibling, to iterate that collection. And in doing so, I minimize my calls to the DOM. Another best practice is to use the selectors API for efficient access to collections. How many of you are familiar with the selectors API that was added in Internet Explorer 8, or CSS selectors in general, the CSS selector syntax? What you can do is you can use the CSS selector syntax inside of your JavaScript to very efficiently go and bring back a collection of items that you can then work on. In this case, I'm calling document.querySelectorAll, and I'm bringing back all required elements. I can then work through that collection very, very efficiently. Then you can see that we're moving our way from networking all the way through the subsystems in the browser. And now we're at the formatting subsystem. The formatting subsystem is the first piece of really what we often refer to as the display pipeline, getting your content to the screen. We now have a well-constructed DOM, and we need to display that. And what formatting does is it takes your document, and it takes all your CSS styles, and it maps those together to figure out what the resulting format of your page should be. One of the best practices here, and again, this really seems like common sense, but you'd be surprised at how many properties on the web don't do this today, is to only send the required styles. This is a pattern that we see quite often, which is a single CSS file that contains all the CSS content for your site. And this is it's kind of funny how often I see this in these types of comments in the CSS, but they'll say, these are the styles for page 1, and these are the styles for page 2. The news websites that we looked at earlier, 4 of the 5 of those news websites don't follow this best practice and send down much more CSS than is needed. In fact, one of those news websites sends down about 5 times more CSS styles that can possibly be used in the page. The problem is that the browser doesn't know this. We actually have to evaluate all of these CSS rules so that we can end up with the resulting format. We have to evaluate all of those rules that are not actually used on the page. So really send down the minimal number. There are some great server-side post-processing tools that will help do that for you if you so choose. This process of applying selectors is extremely complex and in many cases extremely slow, and it happens a lot. There's some things that you can do in your CSS to improve the performance of this, and when possible we recommend that you use class or ID based selectors over element selectors. We recommend that you make element selectors as simple as possible and use child or descendant selectors when able. Let's take a look at a couple of examples of that. So first, use class or ID selectors. Here we have a large chain of element selectors. And what the browser has to do in this scenario when it's trying to format your document is it has to look at every table. It then has to go see if that table has a table row. It then has to go look at the table cell inside that. And then an unordered list, and then a list item. And it has to map this for every table in your document. Instead, you could choose to say, you could use an ID selector. In this case, I have an ID on the table, so I can set it to my ID. And then the browser can quickly map that style to green. The same is also true for child selectors. The last 3 subsystems. So now that we have our document and it's fully formatted and we're ready to display it to the screen, we're going to go through 3 subsystems that are referred to as block building, layout, and then ultimately rendering, or rendering to the screen. I'm going to group these together from a best practices perspective. And the single best practice here, and one of the most important best practices that you'll hear today, is to batch visual changes. In this scenario, you'll see that I have some JavaScript, and I'm calling inner HTML on it to set my document to empty inside this element. I then build up the title and put it inside the element. I then build up the body and put it inside the element, and then build up the footer. In doing so, I actually have 7 inner HTML references. So I'm not following some of the best practices that we talked about earlier. But more importantly, I could end up with up to 3 visual changes. Each time I make a change, the browser is going to attempt to display that to the user as quickly as possible. But I know in my JavaScript code here that it doesn't really make sense to display this element until I have the title, body, and footer together. So I can batch these. And once I batch them together, I can update that inner HTML just once with the resulting contents. I end up with just one inner HTML reference and one visual update, saving a significant amount of time inside the browser. So very quickly in the past 30 minutes, we've gone through the 20 best practices to improve performance. So a quick test. How many of you can name those 20 best practices? All right, I have to go through them really quickly before we transition to the second part of today's presentation. So the first best practice is to compress file downloads. Use conditional requests. Provide cacheable content. Minify your JavaScript. Don't scale images. Use image sprites. Link JavaScript at the bottom of the page. Add a defer tag to JavaScript when you must link it at the top of the page. Link style sheets at the bottom of your page. Avoid using the add import. Minimize walking up that lookup chain. Cache function pointers. Use the native JSON object or native objects whenever possible over other implementations. Remove duplicate scripts. Minimize your number of DOM interactions. Use the most efficient DOM APIs for any DOM access. Use query selector all for groups of data. Only send required styles. Simplify selectors. And minimize page layouts. Now, I wanted to come back to the chart that we looked at earlier, the subsystem distribution across these top 5 sites. And I wanted to call out a couple of things. The first is that site number 1 didn't follow many of the best practices that we talked about for JavaScript. They bring down a whole bunch of JavaScript, which is never executed. It can never even possibly be used in the page. Site number 2 doesn't follow the best practices that we talked about for the DOM or for marshalling itself. They actually cross that marshalling tier a lot, and that really increases the time it takes to load the page. Now, one interesting point here, if you remember from our initial data, is that site number 2 had the smallest amount of JavaScript of all of these pages. They also weren't using any JavaScript frameworks. They had written all their JavaScript by hand, trying to make it as fast as possible. But in doing so, they actually didn't improve the performance of their site. Site number 3 does a fantastic job of caching content. They follow the best practices for every single item on their page. Site number 5 spends a lot of time in the DOM. Every time they need something from the DOM, they cross that boundary and they access it from the DOM itself, and then they often walk the DOM. Site number 4, honestly, site number 4 doesn't really follow any of the best practices that we talked about today, and that's why site number 4 was the slowest to load. Great. So I'm happy to take questions on best practices at the end of the presentation, but I'd like to move into section number 2, which is a preview of Internet Explorer 9 performance. I'm extremely excited to show you guys what we're doing at a deeper level than we covered in the keynote earlier this morning. For those of you who were in the keynote this morning, we talked about hardware-accelerated HTML5. And hardware-accelerated HTML5, and as we took a step back and we thought about what the types of applications that HTML5 would enable, we believed that we needed to re-architect 2 of the subsystems that we just talked about. The first being the core JavaScript engine inside of Internet Explorer. The second being the rendering piece. If you remember back to the display and rendering charts that we looked at, there's a lot of time spent in rendering. And what we've done is we've brought compiled JavaScript to Internet Explorer 9. We've also brought GPU-powered HTML5 graphics. I'm going to show you what these 2 things mean next. And I'm going to do that with a demo. So for those of you who were in the keynote this morning, I'm sure that you saw the flying images demo. I'm running Internet Explorer 8 here, and you'll see that as I move my mouse, I have some images that are trying to follow the mouse. And you'll see that they're moving at about 4, 5, 6 frames a second. And they're having a hard time following me. Now, if I had a CPU meter here, you'd also see that my CPU is completely pegged. The browser is moving these images as quickly as it can. I'm going to go ahead and close Internet Explorer 8, and I'm going to look at Chrome. the same demo. And you'll see that in Chrome, the images are moving at 2 or 3 frames a second, and they're also having a difficult time following my mouse. I'll go ahead and close that. We'll take a look at Firefox. Firefox is much more responsive. It does a much better job, although sometimes it has, there it goes. It can be a little chunky. And when I increase the number of images, you can see that I quickly drop down to about 10 frames a second, 8 frames a second. And it has a more difficult time following my mouse. I'm going to go ahead and skip Safari now for brevity's sake. And I'm going to go to the Internet Explorer 9 platform preview, which during the keynote today you saw we announced, which is the first preview of Internet Explorer 9. And I'm going to look at that same demo, and you'll see it's incredibly responsive. And I'm running at 64 frames a second. I can speed it up, and you'll see that even going faster, I'm still at 64 frames a second. We can zoom in. Zoomed in, still 64 frames a second. We can speed it up while zoomed in, and we're still well above 60 frames a second. Now, your monitor can only display 60 frames a second. And so this 64, 65 number is as fast as your monitor can display this to you as a user. And in fact, this is too easy for us. Let's zoom in a little bit. Let's add some images. We're up to 144 images, still at 61, 64 frames a second. I'm going to go ahead and speed up. This is what we mean by hardware-accelerated HTML5. And this is what compiled JavaScript and GPU-powered graphics enable. I'm going to jump back to the slide deck and talk about this architecture a little bit more about what we've done. I'm going to start with GPU-powered HTML5. Now, when I often say GPU, a lot of you think of hardcore games. Many of you might be gamers or have these really high-end GPUs inside of your machines at home with cooling fans and heat sinks. But everyone has a GPU. Over the past 8 years, every Windows machine has shipped with a GPU on board. And when we were planning the Internet Explorer 9 release, we went and did some research and found that from the Windows Experience Index results, everyone has a pretty decent GPU. You'll see that there's almost all of the GPUs out there score at least a 4 on the index results. The machine I'm using for these demos is actually a 4.5. So this is on the lower end of all GPUs that are out there today. On the left here, you'll see kind of a multi-core CPU. In this case, it's a quad-core. And CPUs are really general-purpose processors. The graphics today inside of all browsers are done on the CPU itself. But when we were looking at HTML5 applications and the types of applications that we expected developers to build, we really wanted to give them full access to the GPU, which on the right here, you'll see a GPU. A GPU is made up of lots of really small, highly specialized silicon processors designed for graphics. There's shaders, there's subsystems designed for alpha blending. And with Internet Explorer 9, we've re-architected our display subsystem to be built on top of the GPU, so that all of the web applications that you build are no longer rendering on these general-purpose CPUs, but are now being rendered on the GPU itself. That's what enables these incredible graphical experiences like you just saw. The second thing that second large architectural change was, of course, for compiled JavaScript. Now, JavaScript runtimes are extremely complex systems. You'll hear lots of acronyms: interpreters, compilers, intermediary languages, JIT. I'm not going to go into that level of depth today. I'm going to give you a high-level overview of what we've done. And that's with Internet Explorer 9, we've built a brand new JavaScript engine that has a brand new JavaScript interpreter. And what this allows is the page to immediately start, or the browser to immediately start interpreting your JavaScript code as soon as it becomes available. In addition to that, we have all the rich the characteristics of a JavaScript engine. We have a brand new set of frameworks that are extremely fast. We have a brand new type system and model for our type system. We have a brand new regular expression engine. But what we really want to enable with HTML5 applications is for that JavaScript code to be compiled into native machine code so that it executes extremely fast. We didn't want to block the initial page load or the foreground process, though, from being able to render your content. And we didn't want to do that compilation in the foreground. But going back to our CPU diagram today, most customers have multi-core machines, and multi-core machines are becoming more and more pervasive. In this case, again, a quad-core. If we look at Internet Explorer 8 and the way that kind of our process model works, and this is the same process model found in almost all browsers out there today. On the foreground, they do all of the, again, the downloading and display and parsing and rendering and interpretation of script. And they do very little on those additional cores. We went back to the data during our planning process, and we found that on average, using the same Windows Experience Index results, almost all customers have multiple cores. In fact, the average today is 2.3 cores per machine, per customer. With that in mind, we decided to take advantage of that additional processing power and compile all of the JavaScript that comes down off the page in the background. We've introduced, you may have heard it referred to as Chakra, which was the code name for our new JavaScript engine, the full background compilation. And what we'll do is we'll compile that JavaScript on the background core. We'll compile it into native code. And as soon as the native machine code is available, the foreground process will take advantage of that, and it will start executing native code rather than interpreting. Here's an example of what happens with in Internet Explorer 9. So again, on the foreground, we'll start interpreting, and we'll do all the parsing, the layout, the page rendering. And then in the background, we'll compile your JavaScript. And then as soon as it's compiled, we'll begin to use that. So let's put it all together. So we've talked about GPU-powered graphics. We've talked about compiled JavaScript. Let's look at what this does to sites. So here's an example website that was loading in Internet Explorer 8. You'll see that this is the CPU time. And then also on the right over here, you'll see that these little purple charts, which is once the page has been loaded, it's going to continue to update visually the page. So that takes some CPU time. In Internet Explorer 9, you'll see that these architectural changes have significantly changed the way that sites run within the browser. You'll see that the page loads much quicker. The native JavaScript execution allows the script later on in the process to execute much more quickly. That's the green pieces down here. You'll also see that once the page is loaded, we no longer spend a bunch of CPU time updating the page like we did in Internet Explorer 8. That's the power of leveraging the GPU for graphics. Now, I also wanted to put it all together for you for that flying images demo. You remember in Internet Explorer 8, it was running at about 5-6 frames a second. It was taking quite a bit of work to update the display. Here, you'll see the Internet Explorer 8 CPU chart. In green, we're interpreting JavaScript. We then change the location of the items and do a layout. In purple, we then go to display that to the screen. And then in yellow, we're actually displaying it. And this takes about, on the particular machine that this trace came off of, it took about a half a second to do that process. That's why we can only be 2, 3, 4 frames a second. So let me show you what this looks like in Internet Explorer 9. This is thanks to, again, compiled JavaScript and GPU-powered graphics. At the bottom here, you'll see in green where we're actually executing the compiled JavaScript. It's almost instantaneous to figure out where we need to move the images. We then have about the same amount of time spent in performing the layout. finally will display it to the screen in the purple and yellow piece. We hand it off to the GPU, and the GPU takes care of moving that for us. Now, I have exactly 13 seconds, but I wanted to show one more quick demo. And this is the most exciting part about Internet Explorer 9. What I have here is the XPerf tools, which ship with the Windows 7 SDK. These are tools that you can go and download today and use to help improve the performance of your websites. I'm going to go ahead and open a trace that I took. Oh, thanks. I'm going to go ahead and open a trace that I took of those flying images. And this is a CPU and a GPU trace. And you'll see here, this is the CPU usage, and down here is the GPU usage. And again, this is for the flying images demo. And I'm going to zoom in a little bit here. And what you'll see is that for moving all of those images around, in this case, I was moving 256 images around, fully zoomed on this machine, I was only using a small fraction of the CPU. In fact, let's zoom in a little more. You can see that here I am using the CPU to calculate the location for the images. Here I hand it off to the GPU. The GPU relays out those images for me. So that flying images demo, again with 256 images, it's only using about a quarter of the CPU on the machine, and it's only using about a tenth of the GPU. And this is one of the things that excites me most about Internet Explorer 9, is really seeing what you as web developers are going to be able to do now that you can leverage the hardware with Internet Explorer 9. So that's all I have for today. I have 30 seconds to take a question or two. And then I'm happy to stick around for some time around the stage to answer additional questions. So anyone have a broad question? Yes? Is this data available to us anywhere? Like look at comparisons that you made? So the PowerPoint presentation that I gave today, the question was, is this data available? The PowerPoint presentation that I gave today will be available. And so all the best practices that I showed, you can go and take a closer look at on your own. The XPerf tool set that I showed at the end here is broadly available with the Windows 7 SDK. So you can go do some of this performance analysis on your own. And then, of course, the Internet Explorer 9 platform preview was released this morning during the keynote. And I would encourage everyone to download the preview and start playing around with what you can do with Internet Explorer 9.
I was wondering about minifying the JavaScript. Is that as important if you've got the HTTP compression on?
So it's a very good question. And yes, it's still extremely important even with HTML compression on. And that's because you're compressing the contents of the JavaScript before the HTML compression kicks in and compresses it even further.
The other question is the compilation of the JavaScript that's done in HTTP5 or IE9. Is that cached after the compilation of the code?
That's something that we haven't discussed yet. The Internet Explorer 9 platform preview that was released today does not currently cache the compiled JavaScript.
Are these profile tools available?
I'm sorry, what was it?
The profiling tools that you use, are they available?
Yes, so the profiler tools that I used right here are available. This is the XPerf tool set, and it comes with the Windows 7 SDK. And of course, Internet Explorer 8 has a built-in JavaScript profiler. The new Internet Explorer 9 platform preview has the built-in network profilers or network analysis tools that we showed earlier.
All right, thank you.
Great. Well, thank you very much. I'm out of time, but I'm happy to take questions around the stage for a while. So thanks again.